and La Nina on the rainfall over southern China in Boreal winter. And my name is Zhang, Renhe Zhang, and from the Chinese Academy of Meteorological Sciences. This institution is attached to China Meteorological Administration, and it's different from the Institute of Atmospheric Physics, where Dr. Lu comes. And the APEC is Institute of Chinese Academy of Sciences. And the contents of my talk includes all these five aspects. And first, I will give a brief introduction about the motivation. We know the El Nino has significant impact on the East Asian monsoon, and through the anticyclone. Through the anticyclone, we know here, and I showed here, and the anticyclone can transport more water vapor to the south part of China. We have more rainfall during El Nino episode in over southern China, and this anticyclone, I think, is first proposed by us in 1996, and we also made some studies on the precipitation in different seasons in the next two papers. And in this paper, and we also investigate if there is a reversed impact of La Nina on the East Asian monsoon circulation. But we didn't find a reversed relationship. That means during El Nino episode, so that you can find the anticyclone here, but you can't find the reverse. For example, the circulation anomaly over northwestern Pacific during the La Nina episode. And some others also show that the impact of El Nino and La Nina on the East Asian monsoon is different, and the significant impact can be found in the El Nino episode, but not in La Nina episode. So our study focused on this, we call the asymmetric impact. And what is the reason for the asymmetric impact? We want to do something on this aspect. And the data and the method used in our study, we used other daily and monthly rainfall data observed in the 355 meteorological stations over southern part of China. And also we use the NSAP NCA reanalysis data and the monthly surface data from NCA, and also the OIR data from NOAA. We defined the data duration is from 1978 to 2010, and we defined the wind half year from November to April. November in the previous years and until the April in the next year. And the El Nino and La Nina, the wind half year of El Nino and La Nina we defined by the Niño 3 index. That's the SST's averaged in the Niño 3 area. And if the wind half year, the average the Niño 3 SSTA is greater than 0.5 degrees, then we take that winter half year to be a El Nino winter. And if it's less than minus 0.55 degrees centigrade, then we take that half year, winter half year, as a La Nina winter half year. And according to our definition, we have 6 El Nino winters in total. That's El Nino winters, and also we have 8 La Nina winters. Winter La Nina during our data period from 1979 to 2010, and here we show the El Nino years and the La Nina winters. The El Nino winters and La Nina winters defined in our study. And now we can let's see the features of El Nino La Nina over East Asia and the Northwest Pacific region. Here we show the composite of the rainfall anomalies in El Nino winters. That's in El Nino winter half year we have 6. We make the composite for the 6 El Nino winters. We can find more precipitation to the south, over south part of China, and the shadings means it's statistically significant. But if we can look at the composite of rainfall in La Nina winter, although we found negative rainfall anomalies, but it's not statistically significant. And very weak negative appears. And we can see that the rainfall is not just a reverse during El Nino and La Nina. And also we check the circulation. Circulation, we know this is anticyclone can be clearly seen in the winter, in the El Nino winter. And this La Nina winter, we can find a weak cyclonic anomaly. During the in the La Nina winter in a lower troposphere, but we can find the anticyclone anomaly is much stronger. I mean the amplitude of the anomalies is larger than the cyclonic anomaly. And we also compared the skewness of meridional winds. We averaged over this area, and we found that in El Nino winter, the skewness is 0.81. It's statistically significant. That means we have this positive means that we have strong southerly anomalies around the east coast of East Asia. But if we also we calculate the skewness during La Nina winter, we found very weak. Although it's negative means northerly anomaly, but it's very weak during La Nina winter, and also it's not statistically significant. And we also checked the other factors, for example, the water vapor flux and the divergence. This is arrows vectors are the water vapor flux. We found associated with anticyclone. We found a strong anticyclonic water vapor flux over Northwest Pacific, and also we found very weak cyclonic during La Nina winter, and we can find the convergence of water vapor over southern part of China, but we found very weak divergence. So from this fact, we can also see the asymmetric features. And here we show the precipitable water and relative humidity in El Nino winter and La Nina winter. We all found the positive precipitable water, and we don't find the significant the precipitable negative anomaly of precipitable water over southern China. And we also, because we know the El Nino, La Nina is associated with sea surface temperature anomalies. Here we show the sea surface SST in El Nino winter, and here is in the La Nina winter. We can find this pattern of El Nino year, and in the La Nina winter, the SST pattern is it's almost opposite. But we also checked the ST anomalies over tropical Western Pacific, and we found that in El Nino year is negative anomalies, SST anomalies, and in the La Nina we found the positive. That's the signal, the sign is just is the reverse. However, if we check the amplitude, we can find in La Nina, the SST anomaly is the amplitude is larger than that in El Nino. That means in the tropical Western Pacific, we have a stronger anomaly during the La Nina winter and a comparatively weak ST anomaly over the tropical Western Pacific. We can also check the OIR anomaly. The OIR means the convection. It's an indicator of the convection. We can find the convection is corresponds well with the SST anomaly. And in the positive, we have in El Nino year, we have negative anomalies, SST anomalies, and we found the convection is suppressed. That's a positive. That's suppressed convection. But in La Nina winter, because the SST is positive, we have a positive ST, and the convection is strengthened, enhanced by the positive SST. And if we compare the amplitude, we can also find the amplitude is larger in El Nino winter than that in La Nina than in El Nino year. So here we can see in El Nino winter, we have a weak negative SSTs in the tropical Western Pacific, and we have weak suppressed convections, but we have stronger circulation anomalies. That's anticyclone anomaly is much stronger than La Nina winter. And in La Nina winter, we have the strong positive SSTs and also stronger increased convections, but we have weaker circulations anomaly compared to the El Nino winter. So why the stronger SST and the stronger convection but weak circulation? I mean the cyclonic anomaly is weak cyclonic anomaly. So in order to give us explanation, we investigate the role of intraseasonal oscillation in the asymmetric impact. Here we show the pulse spectra of the OIR. That's the OIR anomalies averaged over tropical Western Pacific. And here we show the El Nino winter, and this is the La Nina winter. If we compare these two figures, we can find the difference is in the intraseasonal oscillation. During La Nina winter, we have a very strong intraseasonal oscillation, and the intraseasonal oscillation is statistically significant. This line is shows the 95% confidence of the significance. But if we check the intraseasonal oscillation in El Nino winter, there is no signals, no statistically significant signals during the El Nino year. So we can see that is easy to be explained because within the La Nina year, in the La Nina year, we have the stronger convection. We have a higher SST in the tropical Western Pacific, and we have a stronger convection. And the strong convection, we got the stronger intraseasonal oscillation because associated with the convection. But in El Nino winter, the convection is suppressed. So that there is no intraseasonal oscillation in El Nino year. Here I show the variance of bandpass fielded OIR at 10 to 50 days, and the 10 to 50 days are according to the spectrum showed here. We use a bandpass filter to filter our data into 10 to 50 days and also 2 to 7 years. That's the intraseasonal and also interannual. Interannual, we compare the variance in El Nino winter and La Nina winter. And we can find that in El Nino winter, the interannual is dominant. The variance is dominant, much larger than that of the intraseasonal. However, In La Nina year, we found a much stronger variance in intraseasonal time scale, but very weak interannual variance in interannual time scale. Therefore, we also checked the bandpass filter kinetic energy. We also found that in El Nino year, the intraannual is dominant, but the intraseasonal is much weaker. However, in the La Nina winter, we found the dominant feature of the intraseasonal oscillation. And we very weak in the interannual variation. So here we can see that because of in the El Nino year, in the El Nino winter, the interannual is dominant. Therefore, we can find a stronger anticyclone. But during the La Nina winter, the interannual variation is much weak. So in the interannual time scale, we checked the La Nina winter half year. That's in the interannual scale, we found a very weak cyclonic anomaly. And the energy, I think the energy mainly concentrated in the intraseasonal oscillation. Certainly, if we make the average of the in the whole winter half year, the intraseasonal signal cannot be appeared. Cannot appear. And so the winter half average appears the interannual signal. Therefore, we have a very weak interannual variation, and that's a weak cyclonic anomaly to compare the El Nino winter. And we also checked the intraseasonal oscillation by composed amplitude. And we found that in La Nina year, it's much larger. The intraseasonal has a very large amplitude, but in El Nino we have a very weak. And we also compared we make the quantitative compared the difference. We show in the positive phase and the negative phase. All the difference are statistically significant. That means the difference of intraseasonal oscillation between El Nino and La Nina are different with statistically significant. And also, if we can intraseasonal oscillation in La Nina winter and this year in El Nino winter, we can find much stronger anticyclone in La Nina. The SO is much stronger, and we found this here is weak in El Nino. That's just a reverse to the interannual time scale. And if we make the difference between La Nina and El Nino winter for the intraseasonal oscillation, we found the anticyclone and the cyclone. That means the La Nina year is much larger than the El Nino, stronger than the El Nino year. And here we come to our conclusions, and the response of the anomalous rainfall over southern China in winter half year to El Nino and La Nina are asymmetric. We said that's not just the reverse. The positive rainfall anomalies with statistical significance appear over southern China in El Nino winter, but no reversed significant rainfall anomaly in La Nina winter. And the rainfall anomalies in El Nino and La Nina winters are related with the stronger anomalous anticyclone and weak anomalous cyclone over West North Pacific respectively. And in El Nino winter, the interannual variation is dominant, and a strong anomalous anticyclone appear over Northwest Pacific in winter half year. But in La Nina winter, the ISO, the intraseasonal oscillation, is dominant, and the weak interannual variation of anomalous OIR leads to a weak response of anomalous cyclone over Northwest Pacific.